Everyone. Hello everyone. Welcome back to my channel. So in today's video, I'm gonna show you a quick demo on how to simulate a biomass gasification or biomass pyrolysis process using Aspen Plus process simulator. So yeah, without further ado, let's begin. Okay, before I begin, I would like to mention here that I am not really an expert when it comes to biomass chemical conversion processes, biomass thermochemical conversion processes, or even biomass conversion via biochemical process. I'm not really an expert on that because my research are completely different. My research is more on material science based on porous material synthesis, on membrane, gas separation, stuff like that. If I do mention something that are incorrect, I apologize, and please let me know what are the correct terms or what are the correct definition or explanation or mechanism when it comes to biomass gasification, pyrolysis, or even torrefaction processes. But I think before we begin, it's a good idea for us to kind of like know what is biomass and then what is pyrolysis of biomass. This one I get all of this information from this website, and then from this paper by Visconti et al. Was published in 2015. So please check it out. A basic introduction when it comes to biomass. It can be processes via three main categories. The first one is going to be thermochemical, where you need to apply heat, thermal energy, either via via combustion, or maybe incineration, or maybe pyrolysis, torrefaction, gasification, and stuff like that. The second one is basically the chemical processes, where maybe the lignin or maybe hemicellulose is being converted chemically to become something else. And then biochemicals, probably where you use a biocatalyst or maybe enzyme to kind of convert all of this lignin, hemicellulose, cellulose into sugar, sucrose, stuff like that. As I said, I'm not really an expert on this, but if I say something that are wrong, please let me know. But in our case, in our simulation, we're going to focus on the thermochemical processes where it involves thermal energy and heat. Of course, there are different classification of there are different way for us to process biomass thermally. For example, we can use a combustion. Basically, we just burn the biomass, or we can use a gasification where you still have some kind of like air to convert some of the biomass. Pyrolysis, as well as torrefaction. This torrefaction is a more recent, I would say, processes where you basically have a biomass and you remove some of the volatile matter as well as some of the moisture to improve the biomass, I would say, fuel quality or maybe energy density of the biomass. But again, I'm not an expert on this. I'm only an expert when it comes to simulation. So what is pyrolysis? This is the process that we will focus on today. Pyrolysis, according to the paper, okay, not my definition, according to the paper, they say that pyrolysis is a thermochemical decomposition process at elevated temperatures, so at higher temperature in the absence of oxygen. So basically, there are no oxygen, but maybe you can flow something else because it is in inert atmosphere. Maybe they will flow like a nitrogen or other gases. I don't know, but it is in the absence of oxygen. Um, I think the figures on your right here kind of like capture the whole, I would say, breakdown, or kind of like the sub processes behind the overall pyrolysis or gasification or combustion process. Because when you put your biomass into a reactor, gasifier or maybe pyrolyzer, stuff like that, not only one reaction, not only one process that are happening, there are a lot of processes that are happening concurrently. But in general, they can be divided into several steps. The first one is going to be drying, which occurs between 100 to 150 degrees Celsius, where you will basically remove the moisture, where all of the trapped moisture in the pores and in the walls of your biomass is turned into vapor. of steam, at elevated temperatures. And then at higher temperature, between 200 to 500 degrees Celsius, it is basically a heating without air to make charcoal or char, if you will. These are called pyrolysis. This is the focus of our work. And of course, if you go down at higher temperature between 800 to 1200 degrees Celsius, you can have a combustion. You can also have cracking, where the charcoal can turn into something else. You have tar gases. You can produce hydrogen, CO2, and stuff like that. And then, of course, you will have reduction processes in between 650 to 900 degrees Celsius, where the charcoal will be converted into flammable gases, as I said before, like a hydrogen, carbon monoxide, and and maybe several other gases like methane. I don't know. Again, I'm not really an expert on this, but this is the basic idea. We're going to focus on pyrolysis. So what are we trying to do today? What we're going to do today is quite simple. We will try to simulate a pyrolysis of biomass by considering the pyrolysis reactor or the pyrolysis reaction is occur under thermodynamic equilibrium. Now, just by looking at this, I know what are the reactor that I'm going to use. I'm going to use a Gibbs reactor, which I will explain to you later. But for our exercise, what are our tasks? Okay, our task here is we would like to investigate how char carbon weight percentage changes with respect to pyrolysis temperatures. We're going to vary from 350 to 750 degrees Celsius. And then we also will check how temperature changes the mole composition of pyrolysis gas, excluding nitrogen. Okay, nitrogen will exist as well, but when we do our calculation, we're going to exclude nitrogen from our composition. Basically that's the topic. Okay, why these two where's my cursor? Okay, why these two is because the paper do investigate those, so I would like to make sure that I'm getting the same result or not. All right, I think I talk a lot. All right, what are the information that we need to get? So first thing first, as I said, all of the details here I took from this Visconti et al. Published in 2015 in the International Journal of Mathematical Model and Methods. All right, to be honest with you, I can critique this paper. First of all, there are nothing new. There are nothing novel with respect to these papers. They're just using the same basic block of Aspen to simulate biomass pyrolysis. There's one. Number two, there are also a few parameters that I think the author of this paper kind of like use it wrongly, I guess. I don't know. This is just my impression of this paper. And of course, when it comes to biomass pyrolysis or gasification, there are more recent papers where they use kinetics obtained experimentally. They compare experiment versus simulation. They do validation. There are a more advanced one, but this one is quite simple, where because it's quite simple, so everyone can do this, I would say. And then maybe a more advanced one, maybe they use like a kinetics as opposed to equilibrium. And then there's also like a different pseudo equilibrium kinetics, stuff like that. But that's not really the point. The only reason why I choose this paper is because they are quite simple for me to follow. No, it's quite simple. The paper is quite simple, and then the result, I can do it following whatever provided by the papers with a few changes, and then I can still compare my result and the paper result, apple to apple, kind of. But I don't want to talk about the paper that much. Okay, what are the information that I get from this paper? The first one is the ultimate analysis. These are approximate analysis, correction, ultimate analysis, as well as sulfur analysis. So these are approximate analysis, percentage dry basis. So we have a volatile matter 84.71, fixed carbon 13.94, and an ash 1.35. So, and then you also have a moisture. So a volatile matter plus fixed carbon plus ash equal to 100. So those are dry bases. And then Moisture here is 7.86. When you add all of these four, it's going to be 107.86. Now, the ultimate analysis is basically the elemental composition of the biomass where without moisture, because these are dry bases, where you have carbon, hydrogen, nitrogen, chlorine 0, sulfur 0.01, and then oxygen is 43.98. So these are, when you add all of these together, dry bases without any moisture, it is equal to 100. For proximate analysis, these are proximate analysis, correction, proximate analysis, volatile matter plus fixed carbon plus ash. Basically, those are the dry basis composition, dry basis proximate analysis of the biomass. So you add all of these three components together, it will become 100. Now, when you add moisture, it will become 107.86. And then, of course, we have a sulfur analysis. Actually, the paper does not really do any sulfur analysis, but what are their assumptions? They assume that sulfur within biomass is equally distributed among these three, I would say, component, all right? Where you have a pyrite sulfur, pyritic sulfur, sulfate type sulfur, organic type sulfur. So you have to understand sulfur in elemental sulfur in your biomass does not exist, by itself. It's going to exist either in the form of sulfate, I don't know, maybe calcium sulfate or whatever, I don't know. I don't really know, but they assume that it is equally distributed. So how do they get this number? So basically you have a sulfur 0.01 equally distributed means divided by 3. So you have 0.0033, 0.0033, 0.0034. You add all of these three things together, it becomes 0.01. So that's how all of these three things are connected. Actually, when you add all of these things, these are not equal to 100. You have to add ash as well. Ash should be 1.35. So you add all of these three things together, then it will become 100. I will show it to you later. All right, so as I said, how can we simulate this? The first thing that you have to highlight, your pyrolysis processes does not exist, one step. There are a few smaller steps that are occurring. For example, drying of biomass. Let's see here, drying of biomass. I will simulate drying of biomass using a stoichiometric reactor using this reaction where one wet biomass, the coefficient will be converted is 0 to 0.99214 dry biomass plus X water. So X here is why do I write down X is because I don't really know what is the coefficient for water, but I know how to solve this, no issue whatsoever. So as you can see, all of these reactor that are inside this, I would say maroon, is it maroon? I don't know what are this color. So these boxes is basically all of the minor steps that I have to do in order to simulate gasification processes, where I have a drying process occurs at 150 and 1 bar, and then decomposition is basically a breakdown of the biomass, breakdown of the dry biomass, because you have a wet biomass here, has a moisture. You do drying, so it will have a moisture, steam plus dry biomass, and then you will use a decomposition reactor using R yield, okay, where the biomass will be converted, there will be a breakdown of biomass into its elemental form, I would say, and then using a R yield. In the paper, decomposition equation, they use a user supplied Fortran subroutine for mass balance equation, but I'm not going to use that. But if you can code using Fortran, by all means, you can do that. I'm not going to do it. And then lastly, we will, based on all of this, we will, all of the gases here, all of the gases plus char, ash, whatever, will go into this reactor where equilibrium calculation will occur to produce a gas mixtures that have the minimum Gibbs free energy. In this case, you have inert gas going into this reactor because pyrolysis is basically a process where you can have inert gas but no oxygen. So as you can see here, you have inert gas at 30 degrees Celsius, 1 bar, and the flow rate is 0.5 kilogram per minute. Composition is 99% nitrogen and then 1% of oxygen. So basically, very small amount of oxygen. Feed here is 50 kilogram per hour, 30 degrees Celsius at 1 bar. So what are the reactor that I'm going to use here is basically Gibbs reactor, where how do Gibbs reactor calculates all this? So they will do phase and then chemical equilibrium calculation. So basically they have algorithm where they consider all of the possible combination of gas mixture that give them the smallest Gibbs free energy. So I don't want to go into details how they do the calculation, but the idea here is you have a material going in, you have a material going in also. So based on all of this, their flow rate, their composition, their temperature, they will figure out based on their algorithm, their internal calculation, they will figure out what is the best composition that give me the minimum what is the best composition, or what's the best mixture having a certain composition that give me the minimum amount of minimum Gibbs free energy, so all of your product gases, including char, by the way, and including ash, will be separated using this. It's not really a cyclone. It's basically at the bottom of your reactor. You have a grid where all the ashes and char will be removed, will be collected below. So we're going to simulate using this unit. It's basically a component separator. It's basically a CI solid, non-conventional, and then a mixed component separator. So so the solid residue here is your char, basically ash plus carbon, and then your gas product here will be cooled at from 500 to 300, and then we're gonna cool it one more time using water cool, using another cooler here to 40 degrees Celsius, and then whatever condensed gases or whatever remaining whatever liquid phase that occurs will be removed at the bottom, and then gas phase will be removed at the top. So that's how it works. In terms of property method, the paper use Peng Robinson, so we're going to use Peng Robinson as well. And then we're going to use H-Cool Gen and then DCHA IGT model correlation to calculate a density as well as to calculate enthalpy correlation with as a function of temperature. This is not, okay, I'm not going to go into details here, but if you refer my previous video, you know what I'm talking about. I'm going to use a default one because this is not really focusing on this two model, but I'm going to use a default one. Default value. So what are the major components? So when you do all of this gasification, pyrolysis will produce hydrogen, CO, carbon monoxide, CO, nitrogen, oxygen, methane, water. We're gonna produce char. Okay, for char, we will assume that it is consists of carbon solid. So these are solid. You also have ash, because when you burn something, you will produce ash. So char plus ash will be available under solid residue. So they will have their own composition as a function of temperature. We will compare later. And then in the paper, the pollutant that they are considering is H2S because we have element of sulfur, SO2, SO3, NO, nitrogen dioxide, nitrogen oxide, and then ammonia. So we're going to use all of this in our simulation. I think that's pretty much it. Oh, one more thing. In the paper, in the paper, they say they're going to use a biomass pellet and ash having a particle size distribution of less than 20 millimeters. Now, they don't have the particle size distribution, but I'm just going to assume these are their particle size distribution, okay? Where you have 0.1 weight fraction of your biomass sample having a dimension between 1 to 4, 4 to 8, 0.2, 8 to 12 millimeters, having a composition 35% of your biomass having a size of 8 to 12 millimeters, and then 0.2%, 20% of your biomass having a dimension of 12 to 16, and then 5% of your biomass having a size range between 16 to 20. Okay, why this? Actually, in the paper, they don't really provide a particle size distribution, but the only thing that they provide, that they give information is biomass palette having a size less than 20 millimeter. But I decided to include a particle size distribution because I just want to add more details and then depth to the simulation. Ash also, I just assume having a similar particle size distribution. If you have a different particle size distribution, by all means, use it. I have no issues whatsoever. All right, I think that's pretty much it. Let's go to our simulation, Aspen Plus. I think that's pretty much it. Let me check. Yep. Okay, so let's go to our Aspen Plus simulator. All right, everyone, as you can see, this is my Aspen Plus property environment. The first thing that we need to do is we need to define our components. So I will define my biomass, wet biomass. So I will define them as wet bio. Enter. It will take a bit longer time. Now, conventional biomass is not available in the database, so I will switch the type into a non-conventional component. Okay, and then wet biomass, after it goes into a dryer, you have to it become a dry biomass. You have to define another component, a dry bio. It is also a non-conventional component, so change the type. And then you will also produce ash. So ash is not available in the database. They will also become a non-conventional component. And then the rest are just carbon, char. No, I will you type carbon first. Now, carbon here is basically a solid. Carbon, I assume it is a char, so I will rename this as char. Char here, I assume that it is a solid. Yeah, it is going to be a solid, and it consists only only carbon. The rest, just you have a hydrogen, uh, a nitrogen, you have a sulfur. Just now, from your ultimate analysis, you will also have oxygen. What else? What else do I have? Oxygen, sulfur, carbon is done. And then of course, all of this will be converted into carbon monoxide, carbon dioxide, all the possible component. What else? Water. Oops. WTR. So I'm going to delete this. Delete row. Yes. Carbon, nitrogen. Do I have? I already have oxygen. H2S. My pollutant. SO2. SO3. And O2. NO2. NO. Ammonia. As well as methane. Methane is not actually my pollutant. It's basically my major component of my product gas, pyrolysis gas. I think I have covered all. So hit next. You will be redirected to the component specific to the property method. So choose Peng Robinson. Yeah, Peng Robinson equation of state. I'm not gonna go into detail here, but hit next. After that, you will be redirected to, if I'm not mistaken, let's check. Okay, again, I don't want to deal with this. Just hit next. Let's wait. Okay, here you need to provide information on the properties of your non-conventional components. So the first one is a wet biomass. What are the models that will be used to estimate the enthalpy of the wet biomass? I'm going to use H-Gen. Again, I don't want to go into details. What is this option codes? Please refer to my previous video. These are the default numbers. You have different codes. If you know the information, you can provide your own codes, and you can also provide your own user-specified information or model to estimate the enthalpy of your wet biomass. Density, I'm going to use DCHAR IGT. Again, I don't want to go into this. This is just a model to estimate or calculate density for wet biomass. Now that I'm done, click this drop down. You do the same thing for dry biomass. Click here, choose Gen, and then DCHAR IGT. Okay, done. After that, you click here, choose Ash. The same thing, Gen, DCHAR IGT. So all of it are done. So what I'm doing here is any non-conventional component, you have to provide a model to estimate the enthalpy. Basically, it's a function of temperature. But if you don't want to have a function of temperature, you have a code. You have to change the option code here to give like a what user specific values. And then DCHAR IGT is basically a model to calculate the density. Again, I'm just going to use the default numbers. If you have a different numbers, by all means, you can change the model. And then you hit next. Hit OK. Give it a second. Okay, after that, you can switch to simulation environment. Yeah, my computer is a bit slow, so I apologize for this. Okay, first thing first, the first thing that I'm going to do is I'm going to go to setup. I'm going to go to specification. So what I'm going to do is I'm going to change my stream class. My stream class is basically a conventional. Conventional stream class is basically a stream class that allows you to process conventional component. But in my case, I have CI solid. I also have a non-conventional. I also have conventional component with particle size distribution. If you remember, I have particle size distribution. So what I will do is I will choose this guy. If you refer here, it is a stream that can handle mix, basically a conventional component, CI solid, as well as non-conventional. NC is a non-conventional, and then, but in this case, it is without particle size distribution. So you should choose. I think you should choose this one. Yes, you choose a mix. CI solid as well as non-conventional solid with particle size distribution. Choose this one. Now that you are done, just go back to your flow sheet. Just begin adding all of your units. So I'm going to do this very quickly. Stoic. So this one is drying. The next one is a yield reactor. I'm going to put them here. We're going to use yield reactor to simulate decomposition. And then I'm going to use RGIPS to simulate equilibrium process. Equilibrium pyrolysis process, basically, something like that. wheel. And then I'm gonna use go here. I'm gonna use SS split here, substream splitter, where I'm gonna any CI solid, char, and then ash will be removed using this unit. So here I'm gonna slide down maybe cyclone. And then I have a heat exchanger or heater, if you will. It's gonna be air cool. I have another one. This one is watt cool. Oops. And then the last one is I'm gonna add a separator, vapor liquid separator, basically to remove, basically to separate liquid phase and gas phase. This one is just write down liq SEP set. The next one is just connect all the feed stream. So I have a feed, click here, EED. So here, click here, become dry feed. And then output here become a decomposition product or after decomposition reaction, where I will rename them as DEC, PROD. And then here you have pyrolysis product in equilibrium condition, okay? So I will rename as PRY, PROD. And then I will have inert gas going in, I will have inert gas going into equilibrium reactor. So I will write down maybe inert. Maybe let me make it a bit nicer, I guess. Okay. And then I have here, I will have gas product. And then I have a full gas one. I have a cool gas number 2. And then here I have a gas. Here I will have a liquid phase. And then in here you will have, in here you need to separate a gas phase as well as char. So I will add another one, and then I will rename them as SOLD. Basically, it is a solid residue. So in here I need to reconnect source. Now this is basically the entire flow sheet of my process. I'm not gonna make it nicer, but basically this is how it looks. This is how it's gonna look like. I don't want to waste time to make it, to arrange everything because it's gonna waste my time. I need to charge my battery, so I'll be back in a minute. Right?